So yeah, my presentation is a little bit orphaned in a sense that it's a little bit outside the topics of all the sessions. It should have been in some sort of a systems analysis session because this is what I'm doing in the group of Professor Vlaming. So thank you for having me and letting me party poop your wastewater session. So we are conducting a study where we are mapping the nitrogen, the phosphorus and the protein flows in Flanders. The goal of the study is to identify hotspots of losses of these nutrients and also identify opportunities to improve recycling and reuse of the nutrients, and also link it to how we use proteins in Flanders. The study, or a similar study, has already been executed in 2013. We are repeating it, but we're changing the scope to the food production chain, and we're adding the protein flows, which is a novelty, basically. So the study is in the frame or commissioned by the Flemish government, and is done together with in the lead University of Ghent and other partners. Our role, or my role in this study, is mainly focused on methodology, also a little bit on, also on indicator development and indicator selection. In this presentation, I will talk about the methodology and more specifically the tool that we created to aid in this study. So the model is very high in resolution. It consists of 44 processes, which is higher than what is usually done for these type of studies. And we gathered data for almost 1,000 flows, which is also a lot. And for each of these flows, we have different data points. Let's say we have a mass, a nitrogen, a phosphorus, and a crude protein content where applicable. And to aid with this analysis, also to increase the repeatability and the usability for later use of this study, we developed a custom-made tool that is helping us in doing this material flow analysis. For this tool, we envision it to be an open source tool, so we hope that in the future other researchers will also use it and hopefully also build further on it and improve it. That would be really nice. We're using a couple of well-established frameworks and ecosystems, let's say. The main feature or the main advantage is that we keep all the detailed data very close to our calculations and very close to our modeling. So we can do aggregations, which you always have to do in this type of study, but we can also easily go back to our base data and re-aggregate in a different way. So I would just quickly browse you or walk you through what it does and how it works in different steps, let's say. So first of all, we gather the data. We have done this in this study in just in an Excel sheet in a flat table. We identified the processes that we needed, and we gathered the data for the flows and put this in an Excel sheet. From there, via a module that we developed, we pull this data into our relational database that has a well thought of structure, which you can see here a little bit. And then once we have it in our database and it's ready, let's say, to process, we start refining the data. So for example, we will indicate on which layers we will enforce the mass balances of our model. So we will enforce mass balances for nitrogen and phosphorus, but not for protein, for example. We will also start adding information on the different processes and adding hierarchies. So for example, we have a process, it's called animal production, and we split that out in sub-processes, so pork production, beef production, things like this. Doing it like this, adding this layer of information on these processes also allows us to very easily change the layout of our models. So it's not, we can change that, and it has the advantage that we can adapt the layout of the model to the layout that has been used by other researchers in the past and also in the future, possibly. So for example, there's this Austrian group that did statistical entropy analysis on the food production chain, which we are also highly interested in, and then we can adapt the layout of our model to that stages model that they developed. Or similar for a study that has been done in France and later on also last year in Leuven. They used the generalized representation of the agricultural and food system. Well, we can change our layout to that one too and recalculate then our indicators, and this enables us to compare results. As a next step, we will make our data even more detailed by adding material properties to it, enabling also a deeper analysis, especially for the protein flows. This is interesting because we're interested to know if we have a flow of protein, what is the quality of the protein, for example, what is the origin, is it animal or plant-based, and so forth. So as an example, we have a flow that goes from households to composting, that's the vegetable, garden and fruit wastes. We know more or less an average composition in Flanders of that flow. Well, in our model, we indicate all those materials. And then from there, we link it to external databases. So for example, we have food and feed tables from the USA, from the Netherlands, that are published and can be used openly. It's open data, most of them, not all of them. And we link our materials that we have in our flows to these external data sources. For that, we have then created mapping functions. So if we need a property for a specific material, let's say crude protein, we can pull that from the feed tables, for example, is an application mainly for feed that has this information. Well, we have a function that will tell the system how do you fetch for this database, how do you fetch this specific property. This greatly enhances the repeatability. If we redo a similar study, we don't have to go browse again and look up all these properties. We can just select what material it is, and it can be pulled in. Also, by doing it with these mapping functions, we can keep these data sets in their original shape, how they are published, without having to pull them into our own data structure. Then in the next step, we will do some advanced, well, semi-advanced maybe, statistical analysis. So of course, in a material flow analysis, you want to have your mass balances closed. But if you gather data, it has errors always and uncertainties, and you will notice that if you calculate it, your mass balances will never be 100% closed. As you can see here a little bit, you have this one process, pork production. Well, this is on the upper picture shows what it looks like on your raw data that you have gathered. We want to close those mass balances, and also we want to reduce the uncertainty, and the tool for that is data reconciliation. That we also built into our system. Basically, it means that you will tweak your gathered data or your raw data. You will change the values a little bit in such a way that your mass balances are then closed, and this reduces the uncertainty on your data. There are, of course, constraints. So we will close our mass balances in the 95% confidence interval. We have constraint functions for this, the constraint functions over the processes that are balanced. And we have an objective function, meaning the tweaking of the data has to be minimal, and this uses the weighted sum of least square methods. So this gives us large equations that we then plug into an existing optimizer library in the Python ecosystem. And we let it run, and then as a result, we have, well, if everything is well, we have closed the mass balances and we have reduced the uncertainty on our data. And then in the last step, well, there's other things to be done, but I have to limit it a little bit here. But in the last step, of course, we calculate indicators and we do visualization. And this is the nice thing about our tool. We can do this semi-automatically based on our base data on the raw data without having to first create a tool and then bring it, for example, to Excel or whatever. We can also generate these Sankey diagrams automatically. For this, we use other open source libraries. We plug them into our system, which is, of course, of great help. We hope to use, well, we will further develop this tool and further use it for scenario analysis, ex ante MFA, and so forth. And like I said in the beginning, we hope that other researchers, once we have published it, will use it and maybe build further on it. Okay, thank you for your attention.